Hello everyone. You're going to notice a slight difference with this screencast today, and that is that the webcam is on. Normally I don't use the webcam, but given the circumstances in our new classroom setting, I felt that it was needed. You're also going to notice that I've broken the screencast into two separate segments. There's going to be one for your lessons, and there's going to be a separate one for all the activity guides. I did that because as I go through these lessons, I'm going to have to be a lot more detailed than what I typically am because I'm not going to be readily available to answer your questions after you watch it or read the slides. So this will be a little bit longer than it normally is. In addition to that, the activity guide is going to be split and separated. So that's a separate video that is posted in Classroom with the activity guide for the actual lesson, for the actual project that you guys will be doing to complete this. So with that being said, let's get started. So today we're going to be talking about asynchronous counters with MSI gates. So before we left for our 2-week hiatus, we were looking at asynchronous counters that had small scale integration or SSI. This meant that we were using things like flip-flops to achieve our desired results. We're now moving on to medium scale integration or MSI, where specific chips are used to accomplish the same tasks that we saw with those SSI. That small scale integration. Specifically in this lesson, we're going to be looking at the use of a 4-bit counter. So like I said, we're going to be taking a look at the 74LS93 4-bit ripple counter in this lesson. We're actually going to use a different chip in our simulation just because that's what we have available to us, but we are going to be focusing on the concepts from the 74LS93 because it is the industry standard. We're going to be taking a look at the block diagram, the pin map, the count sequence, and its reset truth table, just so you guys have a really good idea of how this chip works internally. And then we're going to look at an example counter with the actual 74LS93 implementing it, and then talk about the limitations of using this chip inside of a circuit design. So what we're looking at here is the internal schematic of the 74LS93. And you'll notice that the chip is broken into two different sections. One is identified as the divide by 2 section, and the other is identified as the divide by 8. Each section of the chip is triggered when a clock signal changes from high to low. So that's a high to low change. And the sections of the chip can be used together or separately. And each section has a 2-input reset. That's those JKs that you're seeing on the side here. So those are actually 2 separate inputs for the reset. And I'm sorry, I'm using a script this time it's weird. Something that you can't see in this schematic is that the JK inputs, which serve as the 2-input reset, are actually tied to 5 volts. So that's how we get that triggering signal. And so that is what creates the flipping and flopping of these flip-flops. So what you're now seeing is that the 74LS93 can be used as a 1, 3, or 4-bit counter. We can get a little clever with this chip, and we can create a cascade or an external connection between the 2 portions of the chip to create a divide by 16 circuit. So we have the divide by 2 section, which is up here, which is a 1-bit counter, and then we have the divide by 8 by itself, which is a 3-bit counter. When we cascade them together using an external wire, we can create a divide by 16, which allows us to create that 4-bit counter. So we've already taken a look at the block diagram, which is over here on the left. Now we need to take a look at the connection diagram. So this is the pin map from the data sheet. You'll notice a few things about these pins, and that is that it's a 14-pin chip, but it works a little bit differently than other ones that we've seen so far. The first thing you might notice is that normally pin 14 and 7 are where we connect our VCC and ground. In this case, it's actually pins 5 and 10. Additionally, if you look at pins 2 and 3, right here are your resets. So those 2 input resets are right next to each other in pins 2 and 3. And then pin 14 and pin 1 are inputs. Pin 14 is input A, and pin 1 is input B. Be careful to remember that. I personally tend to trip up and think that input A should be pin number 1 because A is the first letter of the alphabet and 1 is where we start counting. But input A is actually on pin 14. Additionally, you'll notice that pins 4, 6, 7, and 13 are all labeled with the letters NC. That means not connected. This means that these pins do absolutely nothing. They are not connected to anything on the interior. As you can see, there's just nothing connecting them to either of the flip-flops inside of here. So if you put wires there, nothing is going to happen inside of your circuit. Additionally, pins 12, 11, and then 9 and 8 are outputs. So we have QA, QD, QB, and QC. Remember that these are a little bit out of sequence. It doesn't go A, B, C, D when you go to start wiring. So if you're going to QD, which is an LED you would have labeled as QD, you need to make sure it's coming out of pin 11. So again, a little bit out of sequence on that side of the pin map. So now we're looking at the count sequence and the truth table. The truth table indicates where we need high and low signals on the outputs in order to count these numbers. So obviously 0 is all lows, and then in order to get 0, 0, 0, 1, we have a high signal on QA. Remember, it's a binary counter. So when those LEDs indicate, they're going to be indicating where you have ones and zeros for these numbers. So that's what we're looking for. Any lit LED is going to indicate a high signal or a 1. An unlit LED is a 0 or a low signal. So, and then just remember that you need a high signal on both of your resets before this will reset and count. So here we're moving into an example. This is kind of similar to a deli counter is what you can think it as. It starts at 0 and it counts up to 12. Technically 13. 13 is where the circuit resets. So what we're looking at is that we have the 74LS93 in the center. It's wired out to 4 LEDs, which count in binary. And then all of these loop through a 4-input NAND gate and 2 different inverters in 2 different locations to create this specific circuit. This is actually the circuit you're going to be designing a little bit later. You can see the clock signal comes in through the input A. Remember, input A is pin 14 on that chip. So then once you go through here, you're going to see that your goal will be to have the circuit count to 12 or 1100. So it would be QD lit, QC lit, QB unlit, and QA unlit. But it actually has to count to 13 in order to be able to reset and begin counting again. So it'll blip 13 really quickly and then go back to nothing being lit. Now what you're seeing here at the bottom of this slide is the timing diagram. We've looked at timing diagrams before with our clock signals because it's the change in the signal that indicates the flip-flop occurring. So if you look closely at QA, down here after we have 12, you are going to notice that it freaks out a little bit. And where the counter is going, and this is where it's actually going to 13 to trigger those resets, to go back to 0 or 0, 0, 0, 0. Now, there are limitations to this IC chip. The trade-off is that when you have all of these flip-flops bundled inside of one package, you don't get as much flexibility in your design. If we have multiple flip-flops, we can kind of move things around. We can alter where our inputs are going, where our outputs are going. We just don't get that flexibility if they're all in one package. And it does mean that we can only use this in certain situations. Specifically, this chip is not presettable. It will always start counting at 0. You cannot make it start counting at 1, 2, 3. It has to be 0. And it only counts up. So really, if you're looking at designing a deli counter where it's going customer 1, customer 2, this is a great IC chip. But if you're trying to design a circuit that's going to do a countdown timer for the ball dropping in Times Square on New Year's Eve, this isn't going to be the chip you want to use for that because it can count down and it has to start at 0. So with that, this concludes the lesson on asynchronous counters with MSI. So at this time, please make sure that you go into Classroom and check out your activity guide and the video there for that. And if you have any questions, send me an email or log into our Google Hangout office hours. See you later.